one PhD scholar in wireless sensor network. So we are glad to have you today, sir. Professor will deliver a lecture on low power design and high speed techniques.
Yeah, very good morning, all.
Good morning, sir. Good morning, sir.
Good morning. Yeah, it's a different occasion, right? We are conducting so many online meetings, and without
Yes, sir.
seeing
Yes, sir.
everyone's face, so many meetings are being conducted every day, and especially the educational field has come up some 10 years, right, because of this COVID. And I thank the organizers for giving me an opportunity for sharing my views on this IoT and how to have a low power, right? Low power and high speed designs in IoT. And as I can see, some 52 participants are there. And I welcome all the participants for this session and hope we'll have some good time here. And since my, the bandwidth is very low here, actually I'm using a Geo, right? A mobile connection. So I will switch off my video. And occasionally I can switch it on, no issues, right? I think for the time being, I'm switching it off. Hope my screen is visible now. Anyone can respond?
Yes, sir. Visible, sir.
Thank you. And may I know your name, sir? The organizer who is organizing?
Bhargava, sir.
Right, sir. Thank you. Thank you, Bhargava. And I'm, as you said, I'm Prabhakar. Presently working in Sri Sairam College of Engineering, Bangalore, Anekal, Bangalore, right? And I have 22 years of experience and have done my PG and PhD from NIT Trichy. And today we will be discussing a few points regarding this low power design and high speed techniques under the topic of design challenges in VLSI and embedded system for IoT applications, right? So that is the topic of this week-long workshop. And yeah, so we are going to speak different things, right? So actually, we are going to speak about 3 different technologies and 1 technique, right? The first technology is VLSI, right? VLSI, of course, everybody knows about it, and something like use of FPGAs, 6, then came SOC, then NOC, and it goes on, right? A programmable hardware and software, right? So that is actually the one-way definition we can give for VLSI, right? Of course, VLSI means different, but for these things, right, we can have a programmable hardware like FPGA. The second technology we are going to speak about is embedded system. So embedded system is again sort of a dedicated hardware software combination for doing a particular task. We can say something like that. The third one is IoT, Internet of Things, which is actually the collection of so many nodes, we can say. And there is our sensor final control element combination, right? The controller combination. And the data, of course, will be passing to the internet cloud. And you will be having databases available in the cloud. Based on the available data, we can take some useful decisions. So 3 different technologies, right? And one technique we can say that's a low power high speed. In each and every case, we should be able to have the low power consumption, because initially when we started our PhD, like the speed is a very important factor, right? So initially that was area, then speed. Now area is not a problem. Area of the IC is not at all a problem. Speed again is not at all a problem. Techniques are there, but the main concern nowadays is actually the power, whether my system is going to consume lower power or not. So in these 3 technologies, we are going to speak about this low power high speed networks. And first we will try to define each and everything. And supposing if you are having, say for example, I have an embedded system, right? I have an embedded system in the sense, I think you might be knowing what is an embedded system, right? Something like a washing machine, which will be controlled by a small microcontroller. So whether I can reduce the power control in the microcontroller or not. So how you can reduce the power consumption of a single controller? The main thing is the hardware architecture is almost fixed, no problem. And the voltage to be given is again 5 volts or something like that, again that cannot be changed. So how I can reduce the power consumption of a processor? The only possible case is I can reduce the frequency, right? Something like even in your systems, you can reduce the operating frequency of your basic clock frequency, so that whether I can reduce some power in it. Supposing if the process is too slow, I need not operate at a higher frequency. So I'm giving a reduced frequency to the processor and it has to work so that there will be a small power consumption is possible. And where the extreme power consumptions, that like where the low power can be felt, in what of the three technologies where the low power can be felt or can be implemented, right? Can be brought out, we can say, is only in VLSI. Because the VLSI is actually a combination of hardware and software, or it has an advantage of having a programmable hardware and a programmable software, right? Say for example, a normal microcontroller will be having, sir? Right, I think I can continue, right? So a normal microcontroller will be having the architecture and all those things. I think you should be knowing it, right? So there should be a DMA controller, interrupt and all those things. And the power consumption, even if it is not used, everything will be provided with some power, right? No issues. But in the case of a microcontroller that is brought inside an FPGA, right? In Altera brand, they call it as NIAS and Xilinx also, they have some power processor or something like that. Where supposing in a microcontroller, I don't want a DMA controller, I can the hardware itself, I can remove it. So that the area will be reduced, the static power will be reduced, the dynamic power will be reduced because of unwanted transitions. So I can have a power reduced power consumption. So what I mean to say is, of the three technologies, the VLSI technology, especially that FPGAs, have the highest scope for power reduction techniques, right? So in this case, we are going to see an overall view of all these things. And in general, what are the power reduction techniques available in VLSI? So that is actually the case we are going to discuss in this session. So this is actually the overall diagram. I think my screen is visible to you. This is taken from the Liblium Smart World, right? So an example where there are plenty of sensors are available in order to measure the complete parameters, the environmental parameters, right? Say for example, I think if it is visible, I will just go through this one by one. Like air pollution is there, right? I think that is the most critical, especially in Delhi, New Delhi, the air pollution reaches above threshold, right? Goes above threshold. The forest fire detection, again, plenty of forest fires are occurring every day. And the quality of some products, right? They have given the wine quality, they said. The offspring's care, right, is possible. Say, for example, the farmers, right? What is the land, what is the water level and all those things. The sportsman, say, for example, a physical care. What is the pulse rate? What is the heartbeat rate of a sportsman? The structural health of a bridge. So there are plenty of things are there to be measured. And why I have to measure all these parameters? If I can measure all these parameters, then I can get an idea about what is the quality of output from those things. Supposing if there is a bridge, if the quality of the bridge is not good, right, it may fail. In that case, I can avoid the problems, right? Say because of the, the breakage in the bridge. In a similar way, supposing if the pollution is measured, then I can safely stay inside. I can safely stay inside without going out, right? And there are some areas smartphones can be detected, right, where smartphones are not allowed, something, right? The perimeter access control, we can control the access to a security point, right, something like that. So there are plenty of things are available. We need not go through all these things. And the levels may be different. And yeah, and each and every case, there are plenty of parameters are being measured. And what is the, why we need to measure all these parameters? That is because you can get some useful information about this. Actually, one case is something like a street light, smart lighting. So in the case of street light, what happens? Supposing if there is enough light because of the sunlight, right? Then I can switch on the street lights after some time so that I can save the power. And again, in the case of intelligent shopping, it will be increasing your quality of life, right? So there are plenty of things are available. I think we need not discuss about in detail. But the ultimate point is we can have plenty of sensors to make our life easy. And this slide gives an overall idea about this IoT. So the bottom world is again the sensors, whatever the 50 sensors available in the previous case. They are listing some 50 sensors which are very useful in a smart city. And all those sensors are sitting on the left-hand side of your sensing components, this section. I think my cursor is visible to you, right, this section. And on the right-hand side, if you want to control something, right, so there is some control elements are available here. Say, for example, if you want to measure some traffic, then I can have a traffic light controller here. So there are some controlling parameters are there. And these informations are passed to a communication world. There is actually an intermediate edge computing kind of thing, where this is connected through a WAN, through Wi-Fi, or it can even from Bluetooth or UWB, whatever it is, RFID, right? So there are some wireless or wired communications are possible. And from this, the data gets into the internet. And in the internet, there will be a database, the data will be stored, and some persons will be there who is actually an authorized entity, will have the data access, and they will be taking some useful and intelligent decisions. Say, for example, I have a street light here, and at say, for example, at the evening 6 p.m., right, what are the street lights are on? The status will be updated here. And based on the current light available in the streets, right, whether I can switch on the light at 6 o'clock or we can switch it on after half an hour, right? So this person can decide. A simple example I'm saying, right? More complicated things are also there. And since this is a big data, again, the machine learning and AI has also come into picture, right? We will not get into all those things. But basically this useful information retrieval from the available data. And since there are going to be multiple devices are available here, say for example, in the initial days, every person will be having one mobile phone and one laptop, right? So then it happened 2 mobile phones and 1 laptop. Now average person is having almost 7 devices that are connected to internet. That is actually the person is having 7 devices that is connected to internet. That is actually the present scenario. It was initially 1, 2, then it increased up to 6 or 7 now. Now, what is actually the main problem here? Every data is actually, or every device is generating some data, right? You are having a mobile phone will be generating some data. And there are some cameras available that will be generating some data. And each and every data need to be stored here, right? And then what happens actually? This stored data will be become very big. So we are getting into the concept of big data. And how effectively I can handle the data, or how effectively I can take some decisions from the data, bulk data available. In order to go for that, we are going into data science is possible, machine learning is possible, AI is basically possible. So all this data processing is again done. So this is actually the overall scenario where I will be having some IoT devices connected to the cloud. And based on this useful detection, information, I'll be taking some control actions which will be implemented on the bottom side. You can see the control and the operating components will also be available here. Right. Now, if you want to do all these things, the main thing is, especially there in the second layer, I think from the previous slide, I think you can see in the second layer, some processing need to be done here. right? Say for example, if I am getting some bulk data while big data is available, then I should be able to search something, right? I think most of the cases, even our Google servers and all those things they are using the FPGAs for indexing the data available, because I think you should be knowing, right? Basically, the architecture of FPGA enables it to do concurrent processing, right? While the normal microcontrollers or your systems, computers, whatever it is, will be having a single processor. Maybe some threads are possible, of course, or multitasking is possible. But even then, there is a single processor handling all these things. But in the case of FPGA, every point, right, or every block can have a concurrent execution, so that so much of data can be brought in and can be processed simultaneously. So that's why actually we are getting into that FPGAs here for processing this information, and here the data information available here. So for these applications, something like this wireless or voice over the internet or some data multimedia processing, image processing applications, everything, we need a digital signal processing, most probably. We can go for a digital signal processor or any microcontroller, right? Of course, microcontroller, the floating point may not be handled effectively. So we can go for this digital signal processor. So that will be having some fixed memory bus width, and the number of MAC blocks will also be fixed. So in that case, what happens? Since the hardware is fixed, you can only program it only through the programming. The software is programmable, but the hardware remains fixed. If you want to increase the hardware, you have to add one more chip, right? Again, communication will be an issue. So the customization of the DSP is almost, it's very difficult or not possible, we can say. Now, what are the alternative solutions for this? You can go for microcontrollers. Of course, it is very, very small one, right? It is the fundamental one, we can say. On the other end, we can go for FPGAs, ASICs, and SoCs, right? So field programmable gate arrays, and the next one is ASIC, application-specific integrated circuits, and system on chips. Here, you can design your own hardware along with your software, right? As I initially said, you want to bring out a microcontroller inside an FPGA, then what are all the blocks of microcontroller you can decide. And if you want to add some parts, you can add it, or if you want to remove it, you can remove it. And of course, you can design what should be the size of the microcontroller, whether I want an 8-bit microcontroller or I want a 16-bit microcontroller. You can decide your size of your microcontroller. So the hardware are also configurable. And the other advantage is the number of pins available, because most of these devices are having multiple data are coming, right? I think already it's a big data. And the number of devices are also very high. So here actually I can have many number of pins are available, so that I can take the data in bulk and I can process the data. That is, again, when compared to your microcontrollers or DSP processors, the FPGAs will be having the more number of pins, right? And the concurrency, data processing will be concurrent. Again, that is again another advantage. So here what happens? The ASIC and FPGA and SoCs, then NOCs, all these things are actually we can have a customized architecture based on the application what we require, and the functions again can be customized, the bus structure can be customized, or each and every hardware and software can be customized. So this customization should also go with the optimization, right? I have customized, but it is not optimized, then it is going to be a waste. So I'm customizing my FPGA and it consumes lower power. So in that case, my customization is really good. So initially, 3 parameters are there. As I already discussed, area, the power consumption, frequency of operation are 3 important parameters, 3 trios available in the VLSI area. And initially, it was area and frequency were there. But now the power consumption has become very, very critical, and low power designs are the need of the hour at present. And this is actually the VLSI chip power density, right, available. Yeah, I mean, this data is taken in the year 2010, right? I think it is in the period of Pentium. Just I got this data. I think there are i3, i5, i7, so many processors have come nowadays, right? So each and every time, the power consumption is actually getting increased, right? So that is actually the intention of the slide. And the power consumption has to be reduced to some extent, so that most of the devices are mobile now and they are battery operated, right? Say you are having a mobile phone with a powerful processor, and if the battery is not longing for one full day, then you will lose your interest in the mobile phones, right? So the power consumption is going to be a critical factor in all these parameters. And here again, this data may be a good old, right? Maybe up to 2014 it's available here. Gives an idea about what is the feature size in nanometers, the density of this logic transistors, we can say, right? In 1999, it is 6.2 millions and in a square centimeter. And 2014, it was 390 millions, right? Again, the power consumption, the last row, we can see it's 90 watts. And in 2014, it has come to 183 watts, right? So the chip size is increasing. The power supply is reducing. You can see here, the power supply is 1.8 volts, right? Initially, it was working with. In 2014, the power supply applied is only 0.5 volts, right? So there is actually the reduction in the power supply, and each and every time what happens, the power consumption is getting increased. It's keep on increasing. And what are the mechanisms to reduce this power consumption? That is actually the topic of today's one. So here we can see in normal CMOS circuits, most probably these VLSI are made up of bring out of CMOS family, and that will be having the average power consumption, we can say, is consisting of switching power supply, short circuit and leakage power supply, right? What is meant by switching power supply? I think the dynamic power consumption because of charging and discharging of capacitors. When there is a transition between 0 to 1 or 1 to 0 transition, then there will be a power consumption will be there. So that is actually proportional to the number of transitions that occurs. And the short, a momentary period where actually I think you should be knowing, right? What is the CMOS? Is a combination of NMOS and PMOS. And at any point of time, either NMOS or PMOS will be in off state so that there won't be any connection between the VCC and the ground so that the power flow will not be there. But during the transition of 0 to 1 or 1 to 0, at some instant, both my NMOS and PMOS will be conducting. So in that case, what happens? There will be a power short circuit between your VCC and ground. So some enormous power, right? Comparably a larger power will be consumed at that point, right? So here, at some momentary point, the NMOS and PMOS transistors are there. That makes a short circuit there. And the leakage, there will be a small reverse current, right? There's a minimum reverse current that passing through the diodes. So this is actually the power and energy. I think we can skip this one. The dynamic power is consumed. This is what actually I said. I think you can see the diagram here. There is a VDD is connected here. There are some NMOS and PMOS transistors are there. At some point, when the transition is at 0 to 1 or 1 to 0, at some midpoint, what happens? Both the transistors will be there. Both the NMOS and PMOS will be in active state. And in that case, there will be a short circuit between VDD and ground. So whenever there is a transition, then the power consumption will be high. So, or we can say the dynamic power consumption is proportional to the number of transitions that occurs. And of course, it also depends on the load capacitance, right? What is the load capacitance? What is the load driven, right? The capacitance C is available, right? And what is the load available? And this is what I have said, the transition power, the energy, what is the energy consumption? Again, there is a short circuit between the VDD and the ground. And when the transistor switches, both NMOS and PMOS networks may momentarily switch on at some point, right? This is actually the short circuit current. The static power, again, we need not bother about the equations, I think, beyond the reach. There are some ratio circuits, right? So in the case of ratio circuit, what should be the length and width, right? Say, for example, what should be the capacity of the pull-up and pull-down resistors, right? Capacitors, right? So in that case, we have to set the size of these things, right? And in that case, we can minimize the power available in the static cases, especially the ratioed circuits, right? So there is a pull-up and pull-down ratios are there. There will be a weak pull-down and a strong pull-up should be there, right? So that the power consumption can be reduced, something like that. And in the case of low power design, you can see the reduction in the dynamic power. That is actually possible. And this can be done by clock gating, right? Normally, the clock determines what is the power consumed, as I said, in the dynamic power. And supposing if the dynamic power is very high, right? In that case, if the number of transitions is going to be very high, then the dynamic power consumption will be very high again, which can be reduced by gating the clock. Supposing if the gate is connected, I mean, if the clock is given in a periodical way. When there is no data, that clock can be stopped, so that the unwanted transitions can be stopped, so that the power consumption can be reduced. And we can go for comparably small size of transistors and the short wires for this clock. And what is the lowest possible voltage available? So that again we can have it. And what is the lowest possible suitable frequency? So by having these 4 parameters, we can reduce the dynamic power that is consumed during the operation of an FPGA, we can say. And in the case of static power, we can have a selectively use ratioed circuit. In a normal circuit, we can go for a ratioed circuits. And we can use low VT, that is the threshold voltage can be reduced. Say, suppose if I can operate at 5 volts, then I can reduce the voltage to say for example 3 volts or something like that, right? So if you can reduce the threshold voltage, then I can save some power. And the leakage reduction, so stacked devices, instead of a single device I can stack more devices, and we can have some biasing circuits, and operating temperature can be minimized, because as the temperature increases, power consumption also increases. So by using these methods, of course, we can reduce the static power. So basically the low power design will be having the reduction in the dynamic power as well as reduction in the static power. And when designing a circuit for this, right? So what are the design levels for a low power design? We can have some system level designs, right? So I have to find out by what means I can reduce the power consumption of the total system. And then algorithmic, which algorithm will consume lower power, or which model will be consume a lower power. Then RTL coding, when you are designing a small circuit, the RTL level itself, you can reduce what are the techniques for reducing the power. Say for example, I can give one simple example here. Supposing I am having a condition, right? If A is equal to greater than B, then some operation is actually done there. And at some point of time, what happens? If A is less than B, I have to retain my previous value. So in that case, I have to include one register in between. So if there is one register, then that increases the area of your total circuit. And for each and every clock, the register will be working. So there will be a dynamic power consumption will also be there. So by simply rewriting this program in a proper way, I can reduce the power consumption, both static as well as dynamic power consumptions. So in the RTL programming level, we can reduce the power. And in the gate level, as I said, the dynamics or the size of your gate, right? In the FPGAs, again, will give some power reduction. The circuit design and the device technology, what is the technology that is implemented? All these things are getting into the power consumption level. This is here. The system partitioning again. The system partitioning, which section of your program can be written in hardware and which section can be done in a software. Again, there are some parts, right? Say for example, if you want to implement a e-power exponential term in a FPGA, that is going to have a huge area. But instead, what you can do is you can implement the same exponential function in a software using a simple code. So what you can do is you can decide there should be a hardware and software partition should be there, right? So which section should be implemented in a hardware and which section should be implemented in a software. So there should be some sort of system partitioning can be done. And what should be the size of the buses, and what should be the memory, and what are the IO devices, whether they need it or not, and what type of interfaces. So for each and everything, we can have what is the system available, what are the system components available, so that we can get an idea about what is the overall power consumption of this total system. And in the algorithmic level, we can go for, there are some subsystem level, right? So for example, choice of algorithm. What type of algorithm I can use it, right? Whether I can go for binary or gray code, something like that, we are going to see. What is the word length choices for that? Whether I can manage with 8-bit data or I have to go for 16-bit data, something like that. Then how many model interfaces are there? Because each and every interface will consume so much of data, right? So much of tracks available. And again, implementation, that is the software, what is the processor we are going to use and what is the hardware we are going to use. Whether the hardware is just sufficient to hold my program or not. I have to increase the next level hardware, something like that. And the behavioral synthesis constraints, right? So all these things are some important parameters which we need to consider in the algorithm level designs. And again, in the RTL, we can go for pipelining. I think you should be knowing what is the pipelining. Inserting the register so that the critical path can be broken out. So with the smaller critical path, the data processing will be fast, so that what is the average energy consumed, right, or what is the power consumed can also be reduced by proper pipelining and retiming techniques. Then some model selections, what type of algorithms you can go for, what type of models we can go for. And again, multiple frequencies are there. Say for example, I have two tracks are there. Say for example, I am getting A and B, two inputs are given, and I'll be getting two outputs C and D. The C will be coming immediately, but D will take some more time. So what I can do is I can purposely delay my C also. How I can delay my C? I can reduce the voltage there, so that C and D will be available at the same instant. Now, by reducing the voltage at C, I can reduce the power consumption of that. So this is actually a simple example how I can have multiple frequencies for the reduction in the power consumption and the voltage islands. Again, this is it's available in the new FPGAs. The total FPGA will not work with a single voltage, right? So there will be some thresholds will be available, and some section will be working with higher voltages, some section comparably will be working with the lower voltages. So there will be a voltage islands will be there, so that the effective power consumption can also be reduced. And then the reduction in the switching activity through the transformations, right? So we can rearrange the blocks so that the data flow will be minimized and the switching activity will be minimized. By reducing the switching activity, what happens? Normally the dynamic power consumption can be reduced, right? So these are all some topics or some possible ways where we can have the RTA level power consumption. Then gate level, the clock gating. Instead of giving the continuous clock, I can gate a clock. Whenever there is some operation needed, then I can give the clock, otherwise I can stop the clock. Similarly, I can have gating for power. The power can be isolated from some sections if they are not used. The clock tree optimization, we have to ensure without any glitches, the tree is shared out throughout your chip. And logic level transformations to reduce the switching activity. So these are all a few factors that are actually available for this gate level optimizations. In the circuit level optimization, we can have the transistor size. What should be the size of the transistor that is available here? And there are power efficient circuits designs are there already. It's a research topic. It is also there. What should be the cell design and multiple threshold circuits, right? So different sections of your device will be working at the different levels. Something like that we can try. And multiple oxides, right? So instead of a single layer, we'll be having multi-oxide levels, right? So in the fabrication of your IC itself, you can have different oxides so that the partition will be there. And the SOI, right? So the silicon as an insulator, something like that we can try so that the leakage power can be reduced here. And the multiple cell types on a single substrate, right? So all these things actually comes under the device technology. During the fabrication of the device itself, these things will be taken care for the reduction in the power supply. And basically there are two variations available. The first thing is the technology dependent optimization, right? Say what is the technology that is used? Say for example, what is the size of your device, right? What is the supply voltage with which it can work? And what should be the load it has to drive? What should be the switched capacitance? And what is the data throughput? What is the frequency of data in? What is the data of throughout, right? What is the throughput? So all these things are actually depending upon the technology what we are going to use it. So if you can adjust the supply voltage, or if you can adjust the switched capacitance, and you can adjust the rate of switching, that is the maximum operating frequency, then the technology dependent optimizations can be performed in order to reduce the power consumption. And there are a few things, whatever may be the technology that is used, by slightly adjusting the algorithms, right? I think we are going to see some examples, of course, in this forthcoming slides. By slightly adjusting the algorithms, or by slightly adjusting the concept into a wave pipelining, a normal pipelining into a wave pipelining technique. And we can go for some asynchronous systems. When we go for these devices, whatever may be the technology used for fabrication, we can reduce the power consumption. So this is one simple example how we can reduce the power consumption using this algorithm. We will assume we are going to have a counter. If you go for a 2-bit counter, the normal counting sequence will be something like 0, 0, 0, 1, 1, 0, 1, 1, and again it comes back to 0, 0. So for 4 clock cycles, the number of transitions here is actually 6-bit transitions are there. So per clock, there is a 1.5-bit transition is possible. Instead of a binary counter, if you go for a gray counter, or you use a gray code, then in that case, the sequence will be something like 0, 0, 0, 1, 1, 1, 1, 0. So these two values, of course, will be interchanged. Again, it comes back to 0. And in the gray code, I think you should be knowing for every clock, only 1 bit should change. So after your 4 transitions, I'll be having only 4 clocks, 4 transitions only will be there. So there is 1 transition per clock. So instead of a normal counter, if you go for a gray counter, then the number of transitions will be reduced. So we can conclude that the gray code counter is more power efficient than a normal binary counter. In a similar way, if you go for a 3-bit counter, here on the left hand side, you can see there is a binary code. The number of toggles are available here. Say, for example, in this case, 0, 1, 1 to 1, 0, 0. All the 3 bits are changing here. So the number of toggles here is 3. And the average toggle for one full cycle from 0, 0, 0 to 0, 0, 0, one transition, the average transition per clock becomes 1.75. But in the case of gray code, the average transition per clock is 1. So in that case, actually what happens, the number of transitions can be reduced by using a gray counter instead of a normal binary counter. This is one technique. And of course, FSM encoding, everywhere we are using it. The Mealy Moore machines are there and all those things are there. And in the FSM counter, we will be seeing the probability for each and every case, right? So we will do a small analysis, which state will be having the highest probability. And we will encode that particular state with the minimum size of bits, right? And here you can see there are some 2 into 0.3 and 0.4. So here actually the probability is 0.3 here. Here 1, 1 is changing to 0, 0. So there are 2 bits changing is possible here. Here you can see 1, 1 is changing to 0, 1. So there is a 1 transition, 1 bit transition is there. Here again there is a 1 bit transition is there. So here what happens actually, this 2-bit transition 0.3 and 0.4 are there here. And for these 2 cases, it is 0.1 and 0.1. So this is the average is here, it is 1.6. Instead, if this 1, 1 is brought here and 0, 1 is brought here, now what happens? This 0.3 and 0.4, where the high probability is happening, in that case, I am having a 1-bit transition only. Instead of 2-bit transition here, I'll be having a 1-bit transition here. So if you rewrite this FSM program, if you slightly change the coding format, right, the state value format, then here the power consumption, you can see the number of transition, average transitions, only 1 against 1.6 here. So here actually I have taken a very simple FSM, a finite state machine, and assuming a very low probability here, with this small circuit itself, I can have, instead of 1.6 transmission, I can have 1 transition for every state change. So this is actually the FSM state encoding itself. We can feel some higher power saving. This is another technique for reducing the power consumption. So the same thing, right? In a Moore machine, again, we can have the self loop in the self transmission, right? So that can be stopped. Say, for example, there will be some self loop. Whenever there are some inputs, it will be going on and will be coming back to the same self loop, which can be avoided, of course, in order to save the power. That is again another technique. The another technique is called bus invert coding, right? The bus invert coding, normally what happens, I'm transmitting a data. Say, for example, I'm transmitting a 4-bit data. In that case, I'll be transmitting 1000, for example, right? Say, for example, equivalent of 8 is being transmitted. The next time it is reduced to 111, 0111. So I have to change all the 4 bits. What happens? All the 4 wires will toggle, right? 10002, they will toggle to 0111. So what happens when the number of toggles is more than 2? More than the 50% of your data, what you can do is you can go for partial bus encoding or data reordering. So this is actually the case. Here actually what I am going to do is, say for example, there are so many bit of data is there, assume there are some 32 bit of data. If more than 50% of data is changing, what I can do is, I'll be taking a polarity decision logic, right? and I'll be generating one extra bit here, which will be XORed here. So in that case, what I can do is, I will take the same example, right? The first data is transmitted is 1 followed by 3 zeros, 1, 0, 0, 0. The next data transmitted is 0, 1, 1, 1. Now I have to toggle all the 4 bits. Instead, what I will do is, I will transmit the same data 1, 0, 0, 0, and in order to change that thing, I will be changing the polarity decision logic. So I am going to change only 1 bit. At the receiver end, what it will do is, based on this polarity decision logic, it will automatically change 1000 to 0111. So in that case, the transition can be reduced throughout. So this is actually one technique using which the number of transitions can be reduced when you are especially transmitting the data. And this method is actually called as bus invert coding. So instead of changing all the bits in a bus, I'll be adding one more bus called the polarity decision logic, and the polarity decision logic will be changed so that minimum number of transitions can be done in the bus data. So this is actually another technique. And the next technique is called disabling the logic blocks. Again, there are so many blocks are available, and so many features are also available in the Altera or Xilinx FPGAs, right? You can define your own blocks available, right? So that each and every block can be optimized separately or can be reprogrammed separately. So there is a dynamic reconfiguration is also possible nowadays. So here, the large combinational blocks, normally they tend to dissipate more power because they will be having the higher capacitance. And these logic blocks have continuous input signal transitions, but the output may not be recorded at that time. So what happens here? There will be some inputs will be there, but the output may not be recorded. In that case, supposing if we are having some 32-bit data, right? And if you use a register, then for every data you'll be having a 32-bit registers will be there, and all the transitions will be taking place. All the 32 registers will be giving transitions. So what you can do is, you can enable or disable the block whenever they are in use or not. Supposing if the data, if that particular block is not needed, you can block the clock. You can have a clock gating to that, so that that block will not be used. If you want to have a data output from that, then you provide the data along with the clock so that the data will be getting processed. So you can disable the unused disabling blocks here. This is again one technique through which you can reduce the power consumption and avoiding unnecessary transitions. Here what we have already discussed is, like, the number of transitions is proportional to the number of the amount of dynamic power consumed. So if you can reduce the number of transitions, then the dynamic power consumption will also be reduced. So what here we can do is, the number of designs that certain level transit when they are not required to, right? So that is for functional verification, as they need to satisfy the logical and the functional requirements. And such signals handled properly, and if the logic is tweaked to suppress these unwanted transitions, then that will reduce the power consumption. Say for example, again I can say something like that. Like I'll be having different delay paths. Different paths are available with the different delays. I'll be transmitting a data, and at the output, I'll be getting various values before the final value settles done out the output. So all these values will be getting processed in the next stage. What I can do is, I have to wait till all the data comes in, all the data settles down, then I can open the gate so that the final data only will get processed. So again, this is actually something we call it as glitches available, right? Glitches in the sense, actually there are some unwanted transitions, intermediate transitions, maybe of some nanoseconds, but these transitions of course can be avoided. And if you can avoid the transitions, the huge amount of dynamic power consumptions can be reduced. And I think you should be knowing what is the difference between a latch and a register, right? Normally, when we insert a latches in between as a storage elements, they are actually level triggered. And whenever there is an on state, all the transition that occurs will be passing through or will be saved. But in the case of register, that is actually edge triggered. So only during the edge, what is the value available, that will be considered. So if you want to avoid the glitches during the passage, supposing if you are not suppressing these glitches, what will happen? These glitches will be going on throughout. And supposing if you are having so many latches in between, every latch will be giving so many transitions, and the number of unwanted transitions will be very high. the power consumption is again going to be very high. So instead of going for latches, if you go for registers, which is actually an edge triggered device, during the edge, the value will be either 0 or 1. So in that case, only one value will be passed. I think you can visualize what I am saying, right? If it is a normal class, I can explain all these things. But with the PPT, I am unable to do a simple demonstration, something like that. But I think you can understand, right? So normally that is the main problem with this level triggered devices. All the glitches will also pass through the levels. But if you are using a register, during the positive edge or negative edge, what is the value available? That only will be allowed to pass through. So you can avoid the unnecessary transitions by using this. And this is actually one simple example here. Here actually what we can say is on the left hand side, you can see you can define some programs, right? Say for example, this is what actually I said. Supposing if A is greater than B, you are giving some conditions. If A is less than B, you haven't given the conditions. What happens in that case? The program will assume I have to store my previous value. So it will automatically put some register inside. And this register may not be used because all the time the A may be greater than B. In that case, the register may not be used. But normally what happens, because of this register, and whenever there is a clock, the transition occurs, the dynamic power consumption will be there. So basically what happens, an unnecessary register is there, and for every clock the register will be operating. So the total dynamic power consumption will be very high. And the static power consumption also is high because there is an area increase. So instead of avoiding that, what you can do is, if you can write what is the condition for if true and what is the condition for if false. If both the conditions are written, then the system will not assume a register there. So you can reduce the register so that the area will be reduced, and then unnecessary dynamic power consumptions can also be reduced. This is again one technique while coding how I can reduce the power consumption. Then we can go for a large comparator. This is again another technique. We will assume, say for example, the 11th bit, right? So if it is 10 bits, 2 power 10 is going to be 1024. If 2 power 11 is 2048 bit, and I have to check a condition of 2112 clocks. Normally, how you will write the counter? You will write a counter code like this. If A is equal to A plus 1, something like that, and if A is equal to 2112, then do something. So in that case, what happens? The A value will start from 0000 in a counter, and my target value is 2110. So this 4 digits is compared against the 4 digits. So the comparison is going to be very huge. So instead of this large comparison, what I can do is, I will check till the 11th bit is going high or not. If the 11th bit is going high, then only it crosses the 1024 level. I think you can understand, right? So 1024 bit means 10th bit. And if the 10th bit crosses, I need not count all the values from 0 to 2112 comparisons. I will just take the 11th bit. If the 11th bit is high, then that shows my count has reached 2048. Then I will start comparison from 2048 to 2112. So instead of 2112 comparisons, in this case, I am going to make only 52 plus 12, only 64 comparisons. So compare these two things, 2000 comparisons and only 64 comparisons. So the number of comparisons is reduced by comparing the 11th bit. It is only a coding technique, so that if you can write your coding in a proper way, the number of comparisons will be very much reducing. So there will be a power consumption will also be there. Similarly, the comparator logic will be reduced, right? You need not compare all the bits. Only the 11th bit is compared, and thereafter the remaining bits are compared. So there will be a reduction in the size of your comparator can also be experienced, and the significant power consumption can also be reduced, right? And the resource sharing, again, normally when we are going to design some FPGA circuits, the same block may not be used all the times, right? Say for example, the RTL coding should be carried out in a manner that there are no unwanted or redundant logic, right? Say for example, if you want to do some parallel processing, in that case you can go for some redundant logic. That's not a problem, right? You have to do some parallel work. In that case, you can duplicate some logic. That is again good. But If there is no necessity of a parallel processing, in that case, you can reduce the redundant logic elements, right? And every logic element contributes to power consumption as it has some capacitance attached to it. I think you should be knowing, right? Every line, every track will be having the RC component. The resistance and capacitance will be there. The power consumption will always be there. And this capacitance that can be considered as a low capacitance in some cases, right? So we can reduce this so that by having a resource sharing, you can reduce the size of your device or your circuit. At the same time, you can reduce the power consumption of the circuit, right? So both the static state power consumption as well as the dynamic power consumption will be reduced. So this is actually one such example for the resource sharing. The same adder will be used for both the cases, right? So here actually I have written two adders, but if you can write it in a valid case, right? If you are in a statement where I can check both the statements, only one adder will be there, so that instead of two adders, I can have only one adder here. And this is another technique which we have discussed about how to gate a clock. So normally on the right and left hand side, you can see there is a CK, which is actually the clock, will be straight away connected to the register. Now what I am doing is I am going to connect a gate here from the output. So whenever the D is available, then the clock will be passed through. So I can have a control over the clock. So supposing I want to detach this section from the clock, then I can set my D as 0 so that this data, this clock will not be allowed inside your circuit. This is again another technique. And here you can see one shift register, a simple thing I think. In the normal case, supposing if you want to have a shift register, what we will be doing is you will be having a shift register and will be providing the shift registers all the data, right? I mean, the same clock will be given there. Now, here actually what I'm going to do is instead of 4 shift registers in series, I have, 8 shift registers in series, I am going to have 4 shift registers in parallel way. Now the clock is given there to both, but what I can do is instead of normal clock, I can reduce the clock by 50% because they are running slowly, right? So by reducing the clock, what happens? The number of transitions is actually reduced. That is the one thing. The same architecture, same 8 shift registers, there is no change in it. But by doing it in a parallel way, I can reduce the clock frequency by 50% so that the data will be moving slowly, and instead of crossing 8, I can get the same output at the same time without any problem. So here you can see the clock is reduced by f by 2. So one end this will be going, the other end this will be going, only one will be working, and after the same time I will be getting the output from this. So here the same circuit, but by reducing the clock, the number of transitions in all the 8 shift registers will be reduced. In the previous case, you can see the clock is given here. For every clock, all the 8 will be working. But here in this case, since there is an inverter, only this 4 will be working and this 4 will be working, right? So the clock frequency is reduced. This is another technique. And the pipelining, of course, we know this, right? What is the pipelining? This is actually useful for reducing the critical path, right? So you can insert some registers or latches in between the critical path to break the critical path so that the speed, throughput can be increased. So the power consumption or the energy consumed for processing a group of data, right, that can be reduced. So it reduces the power by registering the input at regular intervals. And the overall net length or the critical path will be reduced, and it also minimizes glitches. This is again a very important point. I think normally you can visualize, right? Say for example, there are some 8 bits are there, and you are giving the data at the input. The output of the 8 bits will be changing to various levels before it settles down to a final value. And this can be reduced in the case of pipelining using some registers. And if latency can be compromised, it is better to have pipeline. But what is the problem with the pipelining? The latency. Supposing if you are inserting one register, then what happens? If there are no registers, immediately the input of the clock, I will be getting the output in the case of combination logic circuit without any problem. But what happens if you insert one register? After 1 clock, I will be getting the output. Supposing if you insert 2 registers, after 2 clocks, you will be getting the output. So the latency level, the number of clock cycles that lapses before the output is coming, will be increasing as you insert more and more registers. And if the latency can be compromised, I think it is better to have a pipelined architecture for reducing the power consumption. This is another method. The another technique is going for synchronous versus asynchronous, especially whenever I am not going to have a continuous data. Say, for example, I am going to insert a pen drive in the system. Now what happens? The pen drive may not be available at all the time. So I need not clock the USB port all the time. Similarly, I am going to print some data. So the printer may not be useful at all the time. So whenever there is a bulk data that is available but not regularly, in that case, instead of going for synchronous systems, we can go for asynchronous systems. I think this slide can give an idea about what is the difference basically between a synchronous system and asynchronous systems. On the left hand side, you can see there is a transmitter and receiver. You can assume there is one block which is transmitting, other block is receiving, and they will be having a global clock. And they consume more power than necessary, because even though there is no data available for transmitter to transmit, since the clock is changing, everything will be changing, right? Because this circuit is driven by a clock, not by the data. That is actually the main case. And the clock skew is again a big problem. I think clock skew is actually the irregularity in the timing of the clock to reach different points of your circuit. That is actually called as clock skew. So whenever we can have a high density circuit, normally what happens, the clock will not reach all the parts of the circuit at the same instant or same time. So there may be some lapses, there may be some delays available in the reaching of the clock. So the data manipulation will also be different speeds. So this is actually one main problem with the synchronous circuit. That is actually the clock skew. And as I already said, the synchronous circuit works on the critical path, right? What is actually the total path? Say, for example, if the critical path is 5 seconds, and I have a digital circuit, and if I give the data at the 0th second, just I am giving an example, right? It may not be 5 seconds or so, right? It's a big number. And say, for example, I am giving a data at 0th instant, I am getting the output after some 5 seconds, you can say, right? And normally what happens, you can give your next data only after 5 seconds. Otherwise, what will happen, this data and the previous data may collide together, because everything is going to be a voltage transitions. So the voltage transition at the input may disturb the previous data. So your output will be, erroneous output you will be getting. So in that case, what happens is, you can give the next data only after the previous data has safely come out of your circuit. So the critical path is determined by the speed here. So that determines, the critical path determines the speed. On the right hand side, you can see we have an asynchronous system. In the asynchronous system, there is no clock, right? So if only data is available, that will be working. On the left hand side, if the clock is available, that will be working. That is useless. Even if the data is not there, if the clock is there, it will be working. That is actually not necessary. On the right hand side, you can see only if the data is there, it will be working. Otherwise, everything will be idle. That is the first advantage. The second advantage is, instead of a clock, we are going to have a request and acknowledgement. And this two handshaking will be done. And this, using this handshaking, the data communication will be effective. All right. So here, what happens? What is the actual speed? Say, for example, instead of synchronous pipelining, you can as well go for asynchronous pipelining also. Here, based on the critical model, we can increase the throughput of your system. So that is actually another advantage of this asynchronous system. So when I am going to have, again, I said this is only for if the data is not continuous, right? If I am going to get a continuous data, in that case, the synchronous is better, because I have a single clock which will be operating both the transmitter as well as receiver. But here what happens, the transmitter should work first, then it has to give an initialization to the receiver, then only the receiver will start working. So there is a delay in the processing. All right. So because this need for this request and acknowledgement signal, because here on the left hand side you can see the clock is given to both the things, both your transmitter and receiver will be working simultaneously. But here on the right hand side you can see you can have a transmitter that has to give a signal to the receiver, then it should get the acknowledgement, then only the data will be processed. So there is some additional delay will be there in the case of asynchronous case. So if you want to have a continuous data operation, my data is continuous or plenty of data is available to process, then it is better to go with synchronous, no issues. But if the data is not continuous, I'll be having a bulk data, but it will not be continuously coming. Say for example, printing, right? That's what actually I said. I'll be printing only at whenever there is a necessity, I'll be printing. Otherwise, my printer will be idle. Whenever I am inserting a USB, then I'll be using accessing the USB. Otherwise, that port will be simply it will be idle. So in that case, whenever I don't have a continuous type of data, then I can go for this asynchronous type of signals. So this is actually a simple example how I can implement an asynchronous case. I think there are again, this is a separate topic, right, through which we can get through. I will just try to give an idea, right? I will maybe in some 15 to 20 minutes, I will try to give some idea about what is an asynchronous type of thing. And on the left hand side, you can see there is a push channel. There is a data and request. Both will be there in the same direction is available here. So initially, a request will be placed, and the data will also be placed from the left hand side to right hand side. And on the right hand side, the receiver gives an acknowledgement signal. And the diagram below, you can just see there is a thing called C, right? I think this cursor is visible, right? So there is a thing called C. This is actually called as Muller C element, right? This is called C element, we can say. So whenever the request comes here, the request has to be delayed by this delay. And this delay should be the critical path delay of the combination circuit. Suppose if this combination circuit takes 5 nanoseconds, then this delay should be also equal to 5 nanoseconds. Now what happens? The combination process has given out the data, and at the same time the delay is also completed and the control signal comes here. And this latch will be enabled only if the output from the C is coming, and the output of C is determined by the output from this delay, and another output is coming from the next latch. This is because it has to ensure whether this data is ready to be taken by the next combination circuit. So this output will also be coming here, and this delay output will be coming here. These two are processed in the Muller C element, and only if this has completed its process and this data is safely latched here, I will be getting this output here, and this data will be latched here. And then what happens? This data will be coming out from this latch, and this signal will also be coming out. There is a combination logic again, which is equivalent to, there will be an equivalent delay. And by the time this combination logic works out, the data manipulates the data, this delay process will be over. And this will be given to the next latch only if this delay is processed and the next section is ready to accept the data. So this is actually the architecture of a simple asynchronous protocol where I can deploy the request and the acknowledgement signal in order to transfer the data between a transmitter and the receiver, or using your multiple levels. In the normal case, what happens, supposing if it is going to be a synchronous, then I will be giving some clocks here. Right, again, the latch, it is going to be level triggered. If it is a register, it will be an edge triggered, clocks will be given here. But instead of a clock, I am going to have something complicated mechanism is there. But we can get some good advantages in terms of power if the data is again not so continuous, right? But there are some limitations are also available, right? Especially what are the limitations of implementing some asynchronous circuits in the FPGA? The first limitation is how to test the circuits, because most of the FPGAs commercially available, I think you might be knowing, the Altera and Xilinx, right? So these FPGAs are widely used. And a cartridge is provided, which is mostly taking care of the synchronous designs, not the asynchronous designs. So the testing of the circuit is again a very, very difficult one. The cartridges are not available. And the architecture of these FPGAs are designed only for synchronous designs, not for asynchronous designs. So non-standardized architectures are there. And the design people, it is easy to design synchronous circuits than the asynchronous circuits. So they hesitate to go get into this. And the cumulative delay, this is what I said. So the output will be given to the next stage if only if the next stage is free. Then it will give the acknowledgement only if the next stage is free. So the every time the data delay gets accumulated. So there is a cumulative delay is experienced in the case of asynchronous circuit. That is actually one disadvantage. And the area overhead, as I said, instead of a single clock cycle or a single clock signal, I am going to use a request and acknowledgement, two clock signals, and I have to use a C element in between. So that increases the area overhead of your total circuit. But the main advantage is if my data is discontinuous, if I am not going to give a continuous data, in that case, the asynchronous circuit is very, very efficient or low power consumption we can experience when compared to your synchronous operation. And since I am going to have an asynchronous circuits, I don't have a clock, right? That is actually advantage. Now, if I don't have a clock, normally the clock will be operating at a single frequency, right? Say, for example, 2 megahertz or something like that. I can't change the on time and off time of the clock. But here, I'm taking a simple example here. I'm going to explain you a 8x8 multiplier. On the right hand side, I mean, you can see two data are multiplied, data A and data B. The data A is all zeros, right? On the left hand side, you can see the data B is some whatever may be the number, let it be. My output is going to be 0 because one data is 0. My output is going to be 0. So in that case, referring to the above diagram, this is actually an array multiplier architecture. My no output, no stages are used, right? So no block will be used straight away. I can say my output is going to be 0. And if I am going to have the LSB alone is 1 in the case of data A and data B, in that case my result will be 1, and again no blocks or no stages will be used in the normal array multiplier. And similar way, if I am going to have 1 followed by you can see the last row, right? 1 followed by all values. Similarly, data B also has a 1 MSB followed by all bits. In that case, I'll be using all the complete modules or complete blocks, and all the 7 stages are used. So what I mean to say here is, based on the data, I can take the output at an earlier time. If one of my data is 0, I don't want the multiplier at all. Immediately I can say my output is 0. If I am going to have data like row 2, for last row, LSB alone is 1 followed by all zeros. I am going to use only one stage. The remaining stages are not at all used, right? I think the stages used is here again 0 because only the AND gate will be working. So based on the data input, I am going to have a different stages of operation. Now what I can do is, I will have a check at the data input. I will check the data magnitude. If I am going to have a low magnitude of data, instead of waiting for all the stages to complete, say for example 7 stages are complete, I will take the data at the 3rd stage itself. Supposing if my data is like 1x and 1xx, that is available in the row 3. So in the case, what happens? I'll be getting the output, but not at the same time. I'll be different times I'll be getting the output based on the magnitude of the data. So that's why this concept is actually called as a data dependent delay. If I'm going to have a huge data, all the bits are 1. Right, MSB is 1, so that all the bits need to be processed, I'll be giving the maximum delay. Suppose if the MSBs are 0, right, some 2 or 3 MSBs are 0, in that case, I need not wait for all the blocks to complete its operation. I can take the data at a earlier stage. So I can get my processing quicker by implementing this data dependent delay. Supposing if I'm using a synchronous version of this circuit, then what happens? The synchronous will be having a single clock. So whatever may be the data, I have to wait for the worst case delay. That is, I have to wait all the 7 stages to complete. Then only I can get the data output. But if you go for an asynchronous system where there won't be any clock, in that case, actually what happens? I can have a simple technique in order to measure what is the magnitude of the input data. And if the magnitude of the input data is small, I need not wait for all the stages to complete. I will take the data at an earlier point. And if the magnitude of the data is very big, say all the bits are there, MSB is 1. In that case, I have to wait for the maximum time so that I have to take the full output. So this concept of data dependent delay is applicable in case of asynchronous circuits, which will increase the throughput, and thereby we can reduce the power consumption of this circuit. I think this section we can safely omit, right? That we will be having some minimum time. I think this we can do it. Yes, you can just have the circuit here. Is it possible to understand? I think. Yeah, I think it's very difficult to understand this circuit, right? Maybe will take some more time, but I'll give you an idea about what happens here, right? So the same type of data dependent delay I have implemented here. I hope this circuit diagram is visible to you, block diagram is visible to you, right? So here actually what happens, I will just give you the blocks, right? So there is a source memory is available where all my data is stored. I think my cursor is visible to you and you can visualize what I am showing, right? Then you can understand it better. And I have one concept called same data. Supposing if I'm having a data which is a high data, say for example 1 followed by all the bits, right? That's a maximum data. So I have to wait for all the 7 blocks to work. Supposing if the same data is repeating, then what will happen? I have to do the same multiplication again, right? Say for example 1 1 1 1 8 ones, that is multiplied by all ones again, 8 ones. In that case, I will be getting the maximum output, right? That's not a problem. But if the same data is repeating, I need not wait for the full time. Instead, what I can do is, since the previous data is also the same data, immediately I can latch the data immediately for the second multiplication. So what I have to do is, whether the same data is coming here or not, I am making a check, right? Suppose if the same data is there, then immediately I will get the next clock pulse, so that the previous data output will be, once again it will be latched, so that the second data will also be processed. That is equivalent to that, right? Fine. Now, supposing if it is a different data, in that case, I will be having a delay selector. Now, what is the function of this delay selector? I can have 3 values, right? Say for example, the magnitude is low, the magnitude is medium, the magnitude is high. How I can discriminate these things? Supposing if the MSB is 1, right? I am assuming I am an 8-bit data. If the MSB is 1, what will happen? I can have a value from 0 to 255, right? Whatever it is. Supposing if my MSB is 0 followed by a 1, right? That suppose 7th bit is 1, then only 50%, that is 128 will be the value. So in that case, actually what happens, the 50% of data can be, simply you can omit it if the MSB is 0. And if the next one is there, that is the 6th bit is there, again 50% of the data can be omitted. So in a similar way, based on the which MSB is 1 or which MSB is 0, I can divide the data into low magnitude data, medium magnitude data, and high magnitude data. And based on this operation, I can give some delay. Already I have already I have implemented a multiplication operation, and I know what is the timing to complete all the 7 blocks, or 50% or 30%, whatever it is, right? Based on the data dependent delay, the slide we have already discussed. So I have 3 different delays are possible, and I am going to give the delay selection based on the available data, right? And this data will be given to the processor so that I can get the data at an earlier stage. I need not wait for the total stages to complete. That is again one thing. The second thing is I need to generate the delay. How I am going to generate the delay? Say for example, I mean, you can already have seen, right, that there is a delay block is available in the asynchronous case, and the delay should be equivalent to the magnitude of the, I mean, the process delay, right? So that should be equal already. I think you should be seeing that, right? So here what I can do is, supposing I want to have a 10 seconds delay, then what I will be doing is I'll be having a 2-second clock. And if you have a counter to count 5 counts, then what will happen? 5 into 2 seconds, I'll be generating a 10 seconds delay. Right? Supposing I have to use only 3 stages, which is equal to 6 seconds delay, then my counter value will be only 3, because 3 into 2 second clock will be giving a 6 seconds delay. I have a huge data which needs 16 seconds delay. Then what I will be doing? My clock frequency is, clock time period is 2 seconds, and I have to wait for 8 counts, so that 8 into 2, 16 seconds will be reached. So based on a single clock, single time period, I am going to generate different delays. Right? Now, in the circuit, I think you can see whenever the data gets in, there is a free running counter is available here. And whenever the data gets in, what is the count value that will be taken first? Then I'll be generating the delay. And so that I can find out at what time or at what count my output will be ready. If it is a small data, if it is a medium data, if it is a large data. And when the counter reaches that value, I can give out this control signal C1 and C2, which will take the output from the processing model. I think it's a bit difficult to understand. I can feel that. But I think this is actually a concept through which you can have a controller architecture which will be implementing an asynchronous logic, so that I can have 3 things. One is actually you can have a single clock for generating various delays. That is actually one advantage. The second advantage is if the same data is repeating, I need not wait for all the stages. I can take the data immediately. That is the second advantage. The third advantage is based on the magnitude of the data, I need not wait for all the stages to complete. I can take the output from at an earlier point. So by deploying a controller like this, I can take away the data at an earlier speed, right? So whenever I am going to implement such asynchronous circuits, this will be working only if I have a data. Supposing if the source memory is 0, it doesn't have any data, since there is no clock is available, nothing will be working, right? Everything will be stagnant, so no dynamic power consumption will be there. And if the memory is filled with the data, with the data dependent delay, it will be processing the data, so that the average energy consumption, right, for all the data, right, what is the energy consumed instead of power, what is the energy consumed for processing one block of data, can be very well minimized if you use an asynchronous controller architecture along with your process application, right? So this is actually the concept of asynchronous controller. I think we have some variations, right, in the design of these things. I think we can safely skip all these things. And this energy advantages of asynchronous, right? So what are the advantages of asynchronous circuits? So no clock. So the 50% of the clock power can be recuperated, right? Because even though there is no data, since the clock is running, every block will be working. But here, since there is no clock, the unwanted blocks can be simply removed, so that the clock power consumption will be reduced. The automatic shut off of idle parts. Supposing if there is no data, that part will be idle. Only the static power consumption will be there. The dynamic power consumption will not be there. That is equivalent to a perfect clock gating is possible here. And no glitches. So the 50% of power can be saved in the case of combination logic circuits, right? Since the glitches are not allowed here. And automatic adaptation to the power parameter variation. Supposing if there is a voltage scaling. In the case of synchronous circuits, what happens, since the clock is actually running at a different frequency or different voltage. So based on this parameter variation, if the temperature increases, what happens? And the processing will take some more time. But since the clock is running at a faster speed, right, the clock is not affected, say, in that case, I will be getting some wrong outputs. So I think if you have experience in FPGA designs, sometimes you might have experienced all these things, right? Supposing you want to, it will not be there for simple cases. You have to implement some complicated programs, right? Which will be consuming some 20,000 logic elements or 30,000 logic elements. In that case, after some working time, what happens? The same system with the same clock frequency, the system may not work. This may be because the FPGA gets heated up, and because of this heat, there is a delay, change in the delay, and the same clock may not be worked for that delay. So you have to reduce the clock frequency so that your system will be working. But in the case of asynchronous system, what happens since there is no clock available, and the delay is also generated in the same way, whenever there is a temperature, that will also affect the delay, so that there won't be any problems like your synchronous case. And this voltage scaling is also possible. Again, it's a simple, right? Instead of higher voltage, I can go for a lower voltage. That is again possible, right? And the flexibility of asynchronous interfaces, the better use of concurrency can be deployed here, right? Now we can, so far we have seen a few topics regarding this low power design. The next thing is something like low power testing, right? I have to test the total chip design. The testing takes more time than designing, because if the designing takes 2 months, the testing will take 2 months or more than that, because we need to test it flawlessly, right? Especially for the commercial applications, we have to test it thoroughly. And supposing if you want to test an AND gate, so there are 2 inputs are there, so there are 2 power 2 combinations, 4 combinations are there, and for 4 combinations, what are the outputs? If all the 4 combinations, the outputs are right, then you can assume that the AND gate is okay. Suppose if you are having an IC which is having some 100 pins, then there will be 2 power 100 combinations need to be given as the input. Then only you can find out, you can test your complete chip. So again, there are test pattern generators are there. Again, that is VLSI testing is again a separate topic, but you can understand what is the complexity of testing and logic circuit. So that is actually what we have to discuss here. So here, especially in the case of system on chip revolution, challenges both design as well as test engineers. Especially you are going to design the complete system, right? Not like FPGA, you are going to design the complete system. In that case, the design is complicated as well as the testing is also complicated. And the circuit or system consumes more power in test, right? Because the normal data processing, the data may come or may not come continuously. But in the case of this testing, we will be continuously giving the test data. So the system will be working for more time and more power will be consumed. And most probably the transitions, again, we will be discussing it in the next slides, can give rise to several hazards in the circuit reliability, and instant circuit damage may also be happen, right, because of this testing. And this testing cost increases the product cost, difficulty in performance verification, and reduce the autonomy of portable systems and decreases the overall yield. So the testing is again equally critical in the design process. And I think these things we can, why the test power is higher, right? Because the test efficiency correlates with the toggle rate. How will you find out whether my testing is okay? I have to check all possible combinations, all possible ones and zeros, right? So the number of toggles will be very high. And what happens whenever there is a toggling is very high, the dynamic power consumption will be high, so that the overall power consumption will also be increasing. So in the test mode, the switching activity of all the nodes is often several times higher than the normal operation. This is what actually for the test vectors, this will be working high. And the parallel testing is used. And in that case, what happens? Excessive energy power dissipation can be experienced. The design for testing circuitry designed to reduce test complexity is often ideal for normal operation, right? What you can do is the design for testing. You will be adding some blocks in order to test the functionality of your FPGA. Now, that will be used only during the testing, and during the normal operation, this block will not be used at all. But you are going to waste some silicon area for your DFT, which will be causing some static power consumption, right? Because of this leakage power, there will be always some minimum power consumption because of this testing circuits. And these are all, of course, some issues why I am going to consume more power for testing. And I think it's 11:45 now. Sir, whether we can go for some 5 minutes, or I can take up the questions if any. Any feedback from you?
Sir, you please go ahead, sir.
Okay, fine. So I will take some 5-10 minutes extra, right? So what about this internal and external testing? So the power minimization in the external testing, the test vector can be reordered. in a similar way, already we discussed about what is the counter and binary counter and gray counter. So already we have experienced that, right? Supposing if I am going to give a binary sequence, right, we can see the number of toggles or the number of transitions is going to be very high. But if you give the same test vectors in a gray order, right? So for every test vector will be changing in only one bit from the previous test vector. So in that case, the number of interaction, I mean the changes, right, the toggle rates will be reduced so that the dynamic power consumption can be reduced. So for that, what you have to do is you have to reorder the test vector. The same test vector, no changes, but in which order the test vector is given to the circuit, that has to be reordered. Then there is a thing called as cancel reorder. Each and every cell can be reordered, right? Which part of your circuit can be tested, that again can be changed. And there are some extra primary input vectors such that during the scan operation, transition within the circuit is reduced. That is, the test volume can be increased. So you can testing can be done in models, right? So that some part only will be tested, only those transitions will be tested. The remaining part of the test circuits will be tested with the different inputs, right? Because all the inputs will not go to all the blocks, right? So instead, what we can do is which inputs are going to affect which block. Only those sections will be tested, right? So that can also be done here. And there are several BIST techniques, or of course, built-in self-test mechanisms can also be available for reducing this test. Right. So I think, sir, we will stop here, sir. There are plenty of things, right? It will go for another 1 hour. I will give the summary of this, what we have seen here. We started with IoT, and in the case of IoT, we can go for two types of devices. Either we can go for embedded something where we can deploy a microcontroller, or we can go for FPGA. And in the case of microcontroller, the power design, your low power design is almost minimum, right? I mean, the possibility of reducing the power. The only option is we can go for a reduced frequency. But if you go for an FPGA, then there is a plenty of opportunities for reducing the power in terms of design and all those things. So I have discussed so many methods by which you can reduce the power consumption in FPGAs for different applications like IoT. So this is what actually I want to give my summary for this, right? So I think here we conclude the session, sir, and I want to take up any questions, if any, there.
Participants are requested to ask if you have any queries.
Shall I close the screen sharing?
Prabhakar sir, thank you, sir.
Okay, sir. Fine, sir.
Thank you.
All right, sir. Thank you, Amish.
Thank you for your informative session, sir.
All right, sir. Fine. Yeah.
Participants are requested to fill the attendance form has been posted in the chat box.
Sir, shall I leave, sir?
Yes, sir.
Okay, sir. Thank you.